So while everything has London dispersion forces, not everything has the same amount or strength of London dispersion forces. So let's take a look at some factors that affect the strength of these London dispersion forces. The larger the atom slash molecule, the more LDFs. So for example, if you take a look at your noble gases from helium to neon to argon, krypton, then xenon, and then you take a look at their molar mass, right? As we move down the periodic table, our molar mass gets down or increases. And then their boiling point in Kelvin also increases, right? And the reason that it's increasing is because we have these London dispersion forces. The larger your atom, the more electrons you're going to have, the stronger the London dispersion forces. And it's not really just about the mass, but it's about the size. Bigger atoms are more polarizable. And what that means, what polarizable means, is how easy it is to have some kind of dipole induced onto it. So if you think about something like very small, like a helium atom, the electrons are very close to the nucleus, and so the electrons are tightly held. And so it's hard to push them to one side or another, and so it oftentimes doesn't have any kind of dipole. Whereas when you look at some bigger atoms, such as, say argon or something, its electrons are much further away from it, right? They have a much lower Z effective than something like helium, and so they're held less tightly. And so they're kind of easier to push to one side or the other, and so it's more polarizable. And the same thing with molecules. The bigger the molecule, the more or stronger London dispersion forces you have. So for example, if we take a look at London dispersion forces, they track with boiling point. As we go from the left to the right, we're going to have more LDFs slash a higher boiling point. And something like, C2H6 is going to have a lower boiling point than C3H8, then, C4H10, right? So as we get bigger and bigger atoms or molecules, our boiling point increases because we have more or stronger London dispersion forces. But it's not just the absolute size of the molecule, the shape also plays a role. And the general rule of thumb is the more surface area you have equals more LDFs. Because these London dispersion forces need to be right next to each other in order to induce a dipole. So something like, for example, this molecule where we have this carbon that's highly branched, right? If we think about this, it's kind of like a sphere. And then if we think about like another one of these molecules, I'm not going to redraw it, but if we had another molecule just like that, we don't have a lot of contact area. We don't have a lot of surface area between these interactions, these molecules. So there's little London dispersion force going on between them. Whereas something that's more of like a linear chain molecule, right? All of these two are constitutional isomers, which means that they have the same atoms, just the bonding is different, right? If we draw the kind of overall shape of this one, it'd be kind of more oval-like, and we'd have more surface area. And so you can think about the area where these London dispersion forces can happen, it's much greater. And that corresponds to the boiling point. So for example, the boiling point of the compound to the left is 9.5 degrees Celsius, while the boiling point on the right is 36 degrees Celsius, indicating that the molecule on the right has more or stronger London dispersion forces. And so one thing to kind of keep in track is although the London dispersion forces are the weakest, there can be a lot of them. And so they can actually have higher boiling points than something that has stronger intermolecular forces. So for example, methane CH4 compared to water. Methane has only London dispersion forces. That's the only intermolecular force that it has. Water has London dispersion forces, dipole-dipole forces, and hydrogen bonding. We'll learn about these intermolecular forces soon. So it has a lot more intermolecular forces, right? And if you look at the boiling points that tracks, this is negative 259 degrees Celsius. Oh, oops, my bad. I didn't mean to do water. I meant to do methanol, CH3OH. This is 64.7 degrees Celsius. But then if we take a look at a large molecule such as octane, which is CH3, then 6 CH2s, and then another CH3, so it has 8 carbons, hence octane. This also has London dispersion forces only. And so you might think that methanol having more types and stronger intermolecular forces might have the highest boiling point. Well, that's only true when you compare molecules of similar size. Since octane is much larger, it has a whole lot more of these London dispersion forces, and so it ends up having a much higher or a relatively higher boiling point, right? 125.6 degrees Celsius. So even though London dispersion forces are the weakest intermolecular forces, if your molecule is huge, you've just got a whole bunch of them, and so it can have a higher boiling point than something that has stronger intermolecular forces. Your textbook has some good examples of how this applies to real life. There's a lot of cool natural phenomena that are explained by intermolecular forces. For example, this is how geckos walk on walls, right? How do they stick to things? How do they then unstick their foot? They have in their little feet little feelers. They can, when they want to stick to something, they increase the surface area. Thus, they have more London dispersion forces and they stick. And then when they don't want to stick to that, these little feelers retract and they decrease the amount of surface area. And then so they unstick their little foot. So that's pretty cool. It's also, it kind of explains how Teflon works, at least in part. Teflon is that like non-stick material that's pretty much everywhere, right? Everyone thinks about pots and pans, but it's in all kinds of stuff. They're fluorocarbons. So most polymers, most plastics are carbon-hydrogen bonds. These ones instead have carbon-fluorine bonds. Fluorine is a very small atom, very electronegative, and so it's extremely non-polarizable. And so since it's non-polarizable, it has very weak London dispersion forces, and so things don't stick to Teflon, and that's the whole point of Teflon. As you're watching these videos, make sure you're doing the work-alongs. The work-alongs will have more examples that you definitely want to take a look at.